my name's Mark McCambridge. I'm the State Branch President for Victoria, Tasmania, and I have the privilege of kicking off today. So IHEA acknowledges the Kulin Nations as the traditional custodians on the lands on which our services are located and pays our respects to elders past, present and emerging. And today we have with us Mark Hooper, who happened to pick up the best paper at the recent IHEA National Conference in Queensland. So I'll give you a little bit of a background for those who don't know Mark. Mark's an accomplished engineer and project manager in project management professional with over 2 decades at Echuca Regional Hospital, where he serves as executive project manager. Mark has led major capital works projects, including $65.6 million redevelopment of the Echuca Hospital, and oversees sustainability initiatives, compliance and engineering services. For his sins, Mark was a former board member of IHEA and also an active Country Fire Authority volunteer with nearly 4 decades of service. His career combines technical expertise, leadership and community commitment, supported by engineering qualifications from both Swinburne University of Technology and La Trobe University. Don't know if you want to add anything to that little bio, Mark, but we're in your hands. Feel free to drop questions in the chat and we will go through them at the end of the presentation, and otherwise we'll pick up questions when Mark finishes. So over to you, Mark. Thanks.
Thank you very much, Michael. For those that have got their cameras on, can I just get a thumbs up just to make sure I can know you're hearing me? Great, thank you. All right, so this presentation will go for around about 20 odd minutes, and at the end of it, if we need to flick back through some slides to take questions and answer, we can. We've also got Ben Gill, who is the CEO of Plasma Shield Online, and he's the technology supplier for the basis of this project. So this is the presentation that I gave at the National Conference, and I'll pretty much just deliver it the same way, and then we'll sort of walk through the outcomes and where we're at in the journey. So the presentation is titled Bushfire, Smoke, Energy in Hospitals, or alternatively, we could just summarise it and say we all love clean air, right? So what if we were to say, how about let's improve the air quality in our facilities and at the same time reduce energy? And that's obviously the part that we, the holy grail is if we can make something better and do it for less energy, then it's something that we can aspire to do. So we thought, let's have a crack at that with some of the technology that's available. So it's important that if you've got a bit of an idea around those sorts of things that you try and be nuts with mates. And so what we did is we, through the VHBA and the Race 2030, we had a project funded. It was for 14 months duration. Started only in July last year, so it's only been running a little time. And we've partnered with Adelaide University and Plasma Shield, who are the people that provide the technology. The title of the project is a project that involves the retrofitting of an advanced multimodal air treatment system in a healthcare facility, monitoring energy consumption and indoor air quality metrics over an extended duration. So that's the university people's take on it. Our take is let's have a muck around with some indoor air quality on an air handling unit, see what happens. So I know that all of you good people would check your filtration performance and understand it, right? Because indoor air quality is really important. So we're just going to take a little bit of a walk back in time and refresh ourselves about the things that we know. And at the top of the slide pack, every slide's got this same 4 little squares that we'll go back to reference in terms of what we're talking about. So if we think about air and we think about stuff that's in air, then if you think about particles that are 10 microns, then we'll consider those to be four-storey buildings in size. And therefore, if we consider 2.5 micron particles, then they're equivalent to one floor of that four-storey building. And then if we think about 1 micron, that's about the size of a large refrigerator. And so if we make ourselves small enough where we can see four-storey buildings and large refrigerators, then that's around about where we set our standard at the moment using F9, MERV16s or EPM 180s. But there's a whole lot of other stuff that's floating around that's the size of Coke cans and the size of tiny grains of sugar. And what we wanted to do was say, well, how much of that stuff is there? What can we do about it, if anything? And if we can, let's measure it so that we can try and pass that information on for others. And so that's the basis of the study. So if we have a look at a typical F9, you'll see an F9 filter, EPM1 at 80% means that for a PM1, which is the 1 micron large fridge size particles, this filter should be about 83% efficient. And for PM10, which is your four-storey building, it should catch 95% of the four-storey buildings floating around. So an F9 or a MERV16 or an EPM 180 is the efficiency of that particular filter at around that 1 micron range. And so we don't really do much about these tiny grains of sugar or these Coke cans that are floating around, or do we? Well, if we compare an F9, we've selected that over the years because it has lower cost, it's got a lower pressure drop, and it'll catch about 95% of 0.4 micron, down about 0.4, which is, half of this box up the top. And our HEPAs, we get the 99.995%, but it's of 0.3 micron. And so I think we talk about 99.995% as if it's 99.995% of everything, but it's actually of the 0.3 micron. So the stuff that's, somewhere around the size of, half a fridge, but certainly not down to Coke can size or grains of sugar. So here's a chart that shows us of typical presence of airborne pollutants, and it compares their size. And remember, we're filtering to about here. So everything to the left of our red line is what we currently like to filter. The interesting thing is when you look at the particle distribution in the air, that more than 90% of our indoor air pollutants are to the right of this red line. So we have things that are suspended that fall out of suspension over periods of time, and we've got other stuff that's permanently suspended. And unfortunately, things like positive particles, viruses, the majority of bacteria, odor removal sprays, so those sprays that are used to try and remove odor in your workplaces, carbon particles, dust, grease, smoke, they're all not filtered because they're all smaller than our fridge, a lot smaller than our fridge. Some of them are smaller than Coke cans, and a lot of them are starting to get down to size of grains of sugar. So in terms of what we filter, we've always just set the mark where the red line is based on the economics of what was available and the efficiency and the capability of our plant. So what we did is we had 2 air handling units serving similar areas. And so this is a diagram of the outside air coming in through a fine filter into a supply fan, a heat recovery unit, goes to the wards, return air comes back, is filtered again, heat recovery, and then to outside. And so what we did is we simply removed the heat recovery wheel, the supply air filter and the return air filter, and we put in the bio-HEPA in its place. And so we are going to compare this intervention with the unit that's its twin that didn't have the intervention. and see what happens. And that was the whole purpose of the whole exercise. The blue points are points of measure. And the thing that we've got to keep in mind is that all of our health authorities across Australia, they all want us to have this dilution factor of 2 outdoor air changes for 6 air changes. So in a total of 6, we've got 2 outdoor air changes. And so this outdoor air that's coming in, if it's got a whole heap of things that are smaller than refrigerators, then where does that go? What does that do? What does that mean for indoor air quality? And the purpose of this project was to determine, in terms of the decision point we make around fan energy and filter capacity, there's a balance between our indoor air quality and the infection control capability and the cost to produce that in terms of energy emissions. But what if we could actually also remove odour, remove mould, have infection control, and keep a balance with our energy emissions and our costs at the same time with the newer technology that does a better job? So we remove our traditional heat filters and our heat wheel, and we did some measurements. So this is a before picture, and so you can see the heat recovery unit that was in that plant, and then that's the type of F9 filter we looked at before. That photograph there is actually of that F9 when it was pulled out. It was 2 years old and still looked like it was fresh out of the box. So they've been doing a pretty good job, which was great to see. And in their place went the BioHEPA, which was the plasma shield unit. And we were very lucky because you can see there the geometry of what we put in fitted really nicely with our air handling units. And so they just slotted into place nicely in that location. So now what we've got is we've got a control unit, which has got these fine filters and a heat recovery, and we replace them with our BioHEPA unit. And bearing in mind that the fine filter that were these were based on a PM1 standard, and so we were trying to catch those large fridges floating through the sky. But what's this thing going to do? And so that's what the whole purpose was about. Now, as we all know, these things are really easy to modify. You just cut a bit out of your air handling unit and throw another bit in. So that's where the old heat recovery unit was. And there's the new installation in the new location. So you just click your fingers and it all happens whilst keeping your plant going. The key metrics that were being assessed for this project are particle numbers and concentrations, ultrafine particles, ozone, VOCs, and some other stuff that's floating around in the air. And the results that we're talking about today are predominantly on the top 2 dot points. The project is still continuing, and there is more assessment being done on these other components, but we're specifically going to talk about particle concentrations and ultrafine, and that's because we've just got a limited amount of time. So, air quality. Let's talk about air quality. And stuff happens in air. So remember, if we think about our 4-storey buildings and our large refrigerators, if you live in Mildura and this happens to be your place, this is what can happen to you. So get the dog inside because that's what can happen. Now, our filters, they can deal with that because that stuff there that's coming through the air is, sort of large fridge size. Now, interestingly, we looked at this filter, which was our F9. And remember, for a PM1, it had an 83% efficiency on paper. Well, it turns out, when we measured it, that 13.6% of particles between the 0.3 to 25 microns, so sort of from here that way, 13.6% of these particles pass through, which is amazingly close to our 83%. So we're pretty happy to know that in real life, our particles that we thought our filters were capturing were being captured. When we compare that to our control unit, though, you can see that for the same, for the study air handling unit, the same concentration of filters, 0.004% of those same particles got through the study unit. And so there was a 13% was pretty impressive in terms of what it was doing originally, but to get that down to 0.004 for these particle sizes was a pretty good result. Now, I want to just draw your attention here to the total number of these particles that are the 0.3. So, fridges, half fridge size up to 4-story buildings floating around in our air, okay? And here's a typical sort of day. And the number of particles per cubic metre, let's say somewhere around, 1 to 2 million particles floating around in this representation. So I just want you to remember that number of, somewhere around that 1 to 2 million particles. And then you can see here over these days, as we did some installation. So the first part was removing the heat recovery and then removing the filtration and then installing the bioHEPA filtration. And once that was installed, we pretty much got nothing through. But just remember that 1 to 2 million particles per cubic metre. Now, if we look at ultrafine particles, which is 20 nanometres to 100 nanometres. So now we're starting to get down to grains of sugar up to size of Coke cans. So stuff that's nanometres, not micrometres. And with our existing filtration, we were still getting 8.8% of these particles were passing through our F9. So the F9s were doing pretty well. But on our bioHEPA, we were getting 0.64%. So a 12 times reduction compared to what we're between our study unit and our normal unit. Now, this was all conducted during the non-bushfire period. But then what happened is the bushfire period commenced. And through our study period, we had a serendipitous natural experiment occur. And we just want to make it clear to everyone that's watching, we didn't start the fire, but we did have one. And we know that when you study fire and bushfire smoke in the lab, a lot of these controlled burns don't burn down sheds and cars and plastic tubes and everything else that's out in a normal natural environment. And so studies had been done on controlled burns, but no studies had been done on uncontrolled burns where all of these other nasties float around in the air. And what happens to them? Do they end up in our hospital? Where do they go? So Echuca Regional Health this year, on the 11th of January, we were 78 kilometres from a little place over here called IHEA. And on the 11th of January, a fairly significant fire started in IHEA, 78 kilometres from Echuca. Now, this is a photo that I took at that fire, and you can see we're probably, from the fire truck, we're probably about 70 or 80 metres from the fire at this point in time. You can see how clear the photograph is, but you can also see just how thick the smoke is once you're in that space where the fire's burning. So that gives you an idea of just how much nasties are also floating in the air. Lots of things that are not going to be captured by our filters. So on this particular day, 14th of January, because it takes a little while for the smoke to travel around, and so when it turned up into Echuca, we had 170 million particles per cubic metre of the range 0.3 to 25 micron smashing into our filters. And you may recall a couple of slides back, a typical day is 1 to 2 million. And so we're talking about a 30-time increase on the average particle concentration smashing into our filters. And you can see here that the unit where we'd done the modifications, we virtually had nothing. So this pretty much let nothing through. So In terms of moments of importance, we've discovered something here. We've discovered something. What it is, we're not sure, but we know we've discovered something. Now, if we look at fine particles, which are zero point 0.3 to 1 micron, so we're back over heading this way now. The average filter penetration during the bushfire period that got through our normal control system with our F9s in it, 13 million particles per cubic metre, up to 22 million, but an average of about 13 million. And so when you think about before, where an average day has 1 to 2 million particles in it and we filter 80% of them, on this day, 13 million particles per cubic metre are getting through into our space in our wards. Compared to our intervention unit, where 12,000 particles were getting through. That's not million, that's 12,000. All right, so you can write it in your diary. You heard it first here today. We can do something now about where the red line sits in our particle distribution. What we do in the future and what its cost effectiveness is and what effect that has on human health is all yet to be determined. But we can do something better than we've been doing, and we can do it fairly well. So over the number of days between the 13th, 14th, 15th, 16th of January, you can see that we had predominant smoke still smashing into our filters day after day after day. And, 80 million particles per cubic metre still running into us, yet our intervention unit still sitting there running pretty much at not much at all. Now, was this a surprise? Well, previous laboratory studies where the BioHEPA was checked against some of these known airborne items that are products of combustion had a pretty good efficiency. But it was tested against the portable air purifier, which had HEPA, activated carbon, and UV. And they performed, fairly ordinary. But often you take a small sample and it's hard to replicate in the real environment. And so what we've been able to do for the first time is demonstrate that in terms of indoor air quality, particularly from bushfire-related smoke, this thing absolutely cleans it up and does a really good job of it. Our BMS, we also now, similar to how you would go to your BMS and you might look at temperature or pressure or control valve positions. Years ago, to get pressures, you looked at a magnehelic. Now they're on your computer. Well, we now look at sample count sizes on some channels on our BMS, and you can see that over here is some different sized particles, so we can get the representation of those particles. And then we can see after we've cleaned them up through our unit what's coming through, which is zeros. So this is the new future for us all, should we want to take this on and adopt this sort of technology. So just in conclusion, bushfire incidents can significantly degrade air quality, and they can occur from significant distances away. Highly polluted outdoor air can exist and persist for extended periods. Toxic gases and vapours that may attach to particles can be inhaled and then released into lung tissue by metabolic processes, and we know that this is one of the known aspects of cigarette smoking risk. Particle count measurements provide the most sensitive measure of smoke. We don't actually know what's in those substances, but we know that they're there because we can see lots of grains of sugar and Coke cans floating around, and there's lots and lots of them. But we also know that the BioHEPA filtration will address smoke risk, and it will efficiently remove particles, and it will also act as a catalyst filter and increase the resilience of the air cleaning system. And so that's where we are with the study at the moment. There's more work being done and more information will be published once it comes to light. but the initial results on cleaning air up, particularly from bushfire particulates, was quite impressive, and so we thought we would let everyone know that that was the situation. Thank you.